Okay, let's get started. So, are there any questions since last time? I suppose some people somewhere have questions, but do you guys have any questions about this class? It's the most important thing. No? Okay. So, I'm going to continue where we left off, and I'll talk a little bit about your first assignment, which I already put up on Slack. So I'm going to continue the motivation for why we want to consider interaction testing. So we started off with this example of the sort command, which you could, you want to sort a bunch of things, but you want to possibly customize the sort. So if you want to pass in, I want to sort things in descending order or ignore capitalization, there are many different things that we may want to do. So in particular, if you look at the man page for the sort command, there are 18 flags that you could provide to the sort command, or not provide any if you don't want to. So we worked out last time that there are 2 to the 18 different possibilities of whether or not we provide a flag. So if we provide no flag, that's one option. If we provide one of the 18 flags, that's all 18 other possibilities. We can pick any 2 that we want, any 3 that we want, any 4 that we want, etc., all the way up to all 18 chosen. And how many of you remember what a power set is? You probably should. So this kind of rings a bell. If you have a set of 18 things, what is the size of the power set of those 18 things? 2 to the number of those things. Okay, so that's where that comes from. So do we need to try all combinations? So this is more of a philosophical question. Do we need to test all possibilities? In general, do we have to test them all? In fact, we probably do. Because could it be possible that I provide 17 flags to the sort command, and no matter which 17 that I pick, they always work perfectly, but when I add that last 18th one, now everything goes kaput. Could that be possible? Yeah, that's definitely possible. So if we do try all possibilities, this is something called a full factorial design. There are other names in the literature, but this is the main one for it. Full factorial design literally just means try everything. That's literally what it is. But we're going to make one small assumption, and it's a reasonable assumption. So here's the assumption that we're going to make, and it's so important, I'm going to put it in a different color. Okay? So here's the assumption that we're going to make. We're going to assume something called the sparsity of effects. So this is the assumption that we're going to make. And what is the sparsity of effects? What it means is that if a fault arises in a system, if something goes wrong in a system, it's only the result of a few components interacting. It's not like every single component has to interact in order for something to go wrong. We're going to assume that only a small portion of them, if a fault arises, are due to a small number of components, not a large number. And if we want to look at, say, the fault that's going to arise, I'm going to assume has 2 components in it, or 3 or 4 or 5 or some small number, then we may want to consider how many tests that we want to run. So remember from last time, do we want to minimize the number of tests we want to run or maximize the number of tests? Minimize, right. Because there's an inherent cost in running each one, want to minimize the cost. So these are just some numbers that are best known. So if we look at a fault arising from just one flag, that means that if I go from 0 flags to 1 flag, then if a fault arises, then I only need to test 1 flag at a time. Well, what does this mean? Well, and also, what would the test suite look like if we look at all flag options, individual flags? Well, what we can do is just have a test with all flags off. So basically, a flags with a bunch of zeros. Every flag is not chosen. And then the other test would be every flag is chosen. So if we're making the assumption that a fault that arises comes from one flag, as a result of one flag being chosen, then these two tests will find it. Because if, let's just say the third flag is the culprit, like the third one, that's the one that's causing sort to not work, then what we could do is just say, well, if the first test passes, then having flag 3 being off cannot possibly cause the fault if we're assuming that only one component could cause the fault. But if the second test fails, then that means some flag, maybe the third one, was the result of causing the fault. And if we happen to know that it's flag 3 that may or may not be causing the fault, and we see that test 1 passes and test 2 fails, then that must mean that setting flag 3 on, that's causing the fault. And then we can diagnose why it's causing the fault later. Okay, does that make sense? Do you want me to repeat that? So some people said yes to both questions. So what part was not clear? From the beginning to the end? No, I'm kidding.
What wasn't clear, at least for me, was why, I guess, why figuring, knowing that the interaction of flags 1 and 2 caused the crash.
Right. So the model that we're looking at here doesn't actually tell you what the fault, or what the component causing the fault is. We're just saying that if only one component causes the fault, we'll detect that a fault exists. So if both of these tests pass, then there's no fault in the system arising from one component causing the fault. If 2 components can cause the fault, then this is not sufficient. But if it's only one, then these 2 tests will find it, because we're testing every possibility of one component at a time. If we look at a single component in isolation, say the first one, we're testing every single possibility. We're seeing a 0 and we're seeing a 1. If we look at the second component, we're seeing a 0 and a 1. And same for all of the other ones. So we're only making the assumption for that case that one component causes the fault, which may or may not be a valid assumption. So then what we could do is say, well, maybe one component is not enough. Maybe 2 components are causing the fault. 2 flags are causing a fault. Well, we can get by with 8 tests. So I'm not going to write them out for you because we're going to show how to actually make this later anyway. Yeah, and then for the other ones, if we want to look at all possibilities of 3 components, 4, 5, and 6, we have a certain number of tests that are sufficient. So, but I do want to mention what you want to see for the all pairs of flag options one. So for the first one, every single one choice of component, we saw a 0 and a 1. But for the pairs one, we want to look at pairs of flags. So if I want to look at all possibilities of 2 flags, how many possibilities are there if I just look at 2? Well, what could happen? I can have both of the flags off, so that's a 0, 0. So I want to see a 0, 0 for, I pick 2 flags. Could it be that I have 1 flag off and 1 flag on? Yeah, that could be. So I want to see a 0, 1. What else do you think I want to see?
Both flags on.
Both flags on, so a 1, 1. And what else might I want to see? A 1, 0, right. So here what we're really saying is that in the list of tests, what we want to see is a 0, 0, a 0, 1, a 1, 0, and a 1, 1 somewhere within our tests. With the one choice, we just saw a 0, 1, 1 because we only picked one component. Here, we're picking two. So for that reason, look at the 3 flag options one. How many things do we need to see? Well, we're looking at 3 components, each of which can have 2 different values. So how many things do I need to see in total? Someone said it. Yeah, 8. What about 4, do you think? 16, 5, do you guys need coffee? 32, and 6? 64, good. So, yeah, so those are the number of things that we have to see, but we may not be able to achieve that. So, for example, the pairs of flag options, we got to see 4 things, but I claim we need 8 tests, okay? So, but here's the thing that's amazing. The first 2, we can prove are optimal. We cannot possibly do better than those. So for the 2 tests, that's pretty easy to see. I can't get away with 1 test. With pairs, with the 8 test one, that's not immediately obvious. But for the other 4, we don't know if they're the optimal ones. For the 18 one, it might be possible with 17. We don't know the answer. And of course, as we get to 4, 5, and 6 options, the whether or not these are optimal is less and less likely. It could be way less than these numbers, and it probably is. It's just we've never seen an example that is less. So compare to the number of tests that we had to do before. How many tests did we have to do if we just tested everything? It's literally at the top of the screen. Yeah, 2 to the 18. How does even 276 compare to 262,000 tests? That's a dramatic reduction. So that's obviously a dramatic reduction, but you may be thinking, okay, why are you stopping at 6? Well, why don't you go into 7 or 8 or 9 or whatever? So there was a paper that came out, I think in 2002 now, that did an empirical analysis of if I looked at all pairs of options, 3 choices of 3, choices of 4, 5, and 6, and just looking at empirically how many faults can we actually detect in a real system, what they found is that it is sufficient to look only at less than 6 here. And what does sufficient mean? When they looked at 6 choices of options, what they found is that they can detect over 99% of the faults within the real system. So, and of course, if you look at 5, 4, 3, and 2, we get fewer and fewer percent, but we get fewer tests. So it just depends on what the system you're dealing with is, whether you want a high number of options or do you want a small number of tests. So the main question that we're going to try to ask in this class is, are these the smallest possible? What if, for example, that these weren't flags, but had 3 options each? So if they had 3 options instead of 2 options, how many possibilities would the full factorial design have? Instead of 2 options, each had 3 options. It'd be, what's the amount? 3 to the 18, which is astronomically large. Okay, so we're kind of lucky in this case that we only had 2 options, but in the real world, if we look at, say we're testing user input, we may want to test something in between 2 bounds and then right around the bounds to test off by 1 errors, and we may have 5, 6, 7 different possibilities that we may want to test. So the fact that we're only dealing with 2 is kind of lucky. In the real world, we may have many options. So what we want to answer in this class is, are these the smallest possible? And a lot of the time, sadly, we can't just say this is absolutely optimal, we can't do better. So what we'll try to do throughout the class is try to bound how bad it can get. How many tests do we actually need? And not only that, how do we actually construct these? So in these five different, these six different choices here. So for the single and the pair option, those have known constructions. So the 2-row one is pretty easy. I just tell you a test with all zeros, a test with all ones, and that's it. The pairs one, there's a recipe, if you will, of how to actually make the thing. But the last four, they're constructed randomly in some sense. So there's no particular method that's known to actually make these. We're just going to try something quote unquote random, and hopefully we get a good solution. So there's quite a lot of different algorithms we'll be seeing in this class. Things that are deterministic, things that are randomized, things that copy and paste different things. We'll see a lot of different algorithms for doing this. Any questions on this? We'll talk about the formal in a second.
So on the first one, like where all 5 options is only like 2 tests. So even if we like check like the 2 tests, like aren't we like checking like each like 18 at the end like to see like which one is the difference? So like how can we say like it's just 2 tests?
Right. So I think what you're asking, and correct me if I'm wrong, is how do we actually test this? Like how would we actually do this on a real system?
Yeah. Or like which one is the fault?
Right, that's a great question. So here, we're not actually figuring out which thing is the fault or things that are causing the fault. We're actually trying to detect whether there is a fault. So this type of testing is really good for when you're done unit testing, when you want to test right before you ship to say whether there's something wrong if we do multiple things simultaneously. So we're assuming that each of the components itself is completely okay. It's just that maybe there are problems among multiple components simultaneously. So in fact, in this class, we're not even going to consider the single option because it's kind of just trivial. We just do every test on, every test off. And if there are more options, we just cycle through all of the options, and it's really easy to figure out how many tests you need. So how would you actually test this in a real system? What you would do is, say for sort, you would run the sort command on your data set or whatever, and you just check whether the output is sorted according to having all flags off. And for the all flags on one, you run the sort command with those flags, and you just observe what the output is. If it's exactly what you want, then the test passes. Okay, so an example might be if we're trying to write a piece of software like a PDF reader that works on multiple different operating systems, one component could be the operating system that you're using. So like Mac OS, Windows, Linux. Another example could be, for a component could be, how much memory do you have? So if you have 8 gigs, 16 gigs, 32 gigs, 64 gigs, those are all options. And then maybe the type of browser that you're using. That could be another component, whether you're using Chrome, Firefox, Safari, Internet Explorer, those types of things. So we look at those possibilities and we make a test suite based off of them. And for each one of those, we pick an operating system, we pick a memory config, and we pick a browser, run our test on that configuration, and just see whether it does what we expect it to do. If it doesn't, then there is a fault in the system. Does that make sense? Are there any questions on that? Okay, so let's look at the formal model. So what would it be? What would a theory class be without formal models, right? So the formal model here is we're going to we're going to have a set of k what are called factors. The way the notation that I've used so far is component, but it's the same thing. So factors or components, they mean exactly the same thing. So in the sort example, we had 18 components. So what is k here if it was for sort? Yeah, the number of components. How many components did we have for sort? 18. So k for sort. So for sort, k is equal to 18. Those are the components themselves. So now we have a set of possible values that each component can take on. So v sub f, we're going to denote the set of values that each of the factors or components has. So for the sort command, what did each of the components have? So each of the components was a flag. Well, what are the possible things that a flag could be set to? 0 or 1. So v sub f in the sort case is 0 or 1 in all cases. So for every single component for sort, each one of them is a 0 or a 1. But in the example that I just gave, we could have an operating system where we have Mac, we can have Windows, we can have Linux. For the memory, we could have 8 gigs, 16 gigs, 32 gigs, etc. And then for the browser, we have we have Chrome, Firefox, and let's just say Safari to keep it to 3 each. So for each of the components, quote unquote, we're going to assign to it a set of values. It could be the same values, it could be different values for each of the components. Okay, so a T-way interaction, or T-tuple, so I underlined it because this is actually kind of important because we're going to be talking about interactions throughout the class because the class is called interaction testing. So an interaction is you're going to pick T values, T factors. So like in our OS mem browser example, let's just say T is 2, for example. Then your task is to pick 2 components, let's just say OS and memory, and you pick 1 value from each of the components that you picked. So if we picked OS and memory, what's a choice for an OS and memory? Give me a choice for each one. Windows 16 gig. So we're just going to pick a valuation of each of the components. And yeah, that's a perfectly good example. I could have picked Mac and 32. We just pick 1 from each. So that's an interaction. What we have here, what we want to define is something called a mixed level covering array. So what in the world is this thing? So the array itself is an n by k array. So when I say that, I mean that n is the number of rows or the number of tests in the system, and k, we already figured out before, is the number of components. So what do we want to have here such that for every n by t subarray, we have every possible interaction occurring at least once. I have an example to solidify this. So we look at every possible interaction, so picking any set of t components, and any set of values that you want for each of those, and that interaction has to occur at least once. If it doesn't, we don't have a covering array. If we do, we have a covering array. Okay? T is the strength of coverage. So when we were talking about all pairs of components from the sort example, T was 2. And then we looked at T equal 3, T equal 4, 5, and 6. Okay? And K is the number of factors, and we assume T is less than or equal to K. So let's look at an example, and then we'll take questions. So this, I claim, is a mixed covering array, mixed level covering array. So what do you think the 9 represents here? So if we look, so one of the things you probably should learn from theory classes, if you haven't already, is definitions are your friend. Okay, so let's just look back at the definition. So what is the first thing given to the inside the mixed covering array name? Is n. Well, what does n represent? The number of tests. So, well, where are the 9 here? Well, each of the tests is a row in this array. Remember when I said that the only thing that you really need to know is what a 2-dimensional array is? This is where that comes from. So do we have 9 tests here? Yeah, good. Awesome. So I'm going to erase that. So we know there are 9 tests. Great. So I'm going to skip the 2 for now because that's the strength part. And let's look at the 3, 3, 2, 2, 2 here. And also the fact that k equals 5. Where does the 5 arise in here? What is k? The number of components. Well, where do we see 5 here? Then the columns, right. So we see 5 columns right here. Cool. Well, what about the 3, 3, 2, 2, 2 thing? How many elements does that tuple have? The thing in the parentheses. Inner parentheses, I guess. It has 5 things. Do you think that's a coincidence? No. So let's look at the definition again. So the tuple right here, v1 through vk, represents the size of the number of components. The size of the levels for each component. So if we look over here, we have that the size of the set of values is equal to little vf. And what we have here is v1, v2, v3 up to vk. So that means the number of values for each of the components. So if we look at our example here, this says that the first 2 components have 3 possible values, and the last 3 have 2 values. Is that true? So if we look down the first 2 components, do we see exactly 3 things, or at most 3 things? Yep, so that's good. For the last 3, do we see just 2 values? Yeah, and we in fact get that. Cool. So those parts are okay. Now let's talk about the all-important part, which is the 2. Which is, what is T called again? It starts with stren and ends with k. Okay, so it's called the strength. So what does the strength say to do? Well, T is equal to 2, so how many components are we picking? T is equal to 2. So we pick how many components? 2. Good. Pick any 2 that you want. So someone give me 2 columns in this case. Pick any 2 you want.
First and the last.
First and the last one. Perfect. So But we also have to make this check for all other choices, but let's just do it for this one. So what we want to find is every possible interaction among these two columns that we picked. So how many values can appear in the first column? 3 values. How many can appear in the last column? 2. So if I have 3 choices for the first column and 2 for the last column, how many do I have in total? 6 possibilities. So what we have to look for is 0, 0, 0, 1. What now? 1, 0, 1, 1. 2, 0, 2, 1. Why is there no 2 in the second column there? Because it's not a possible value of the last column. Good. Okay, well, do we see 0, 0 just looking at the first and last columns? Yeah, in fact, we see it here. So we see a 0 and a 0 there. Good. Do we see a 0, 1 somewhere? Yeah, the second row, that's good. Do we see a 1, 0 somewhere? Yeah, so it's the, let's see, 5th row. Oh, the 6th row has 1, 0 again. Is that a problem? No. So the criterion is that each interaction appears at least once. It could appear more times, but at least once. So 0, 0 is done, 0, 1 is done, 1, 0 is done. Is there a 1, 1 somewhere? Yeah, the row before it has a 1, 1. And then I think it's pretty clear that we have a 2, 0 down here and a 2, 1 here. Okay, so those 2 columns are okay. How many other possibilities do I have? How many of you do not know what a binomial coefficient is? So if I have 5 things and I have to pick 2 without repetition, how many do I have in total? Using binomial coefficient. I asked you if you know what a binomial coefficient is. So how many do I have? Well, I have 5, choose 2. Yeah, so 5, what I was asking for is to tell me 5, choose 2. That's what I wanted to see. And in this case, it happens to be 10. So if we check those 2 columns, how many other possibilities of 2 columns do I have left? If I've checked 1 pair of columns, how many more do I have? I have 9. Because there are 10 total, we checked 1, now we got to check the other 9. Do you want to check the other 9? I mean, we could waste class time doing it. Do you want to do it? No. I do want to point something out here. So, can we possibly get away with 8 rows? Hint, look at the first 2 columns. How many possibilities do we have for the first 2 columns? Yeah.
9, so we need at least 9.
Right. So if we look at the first 2 columns, we have 3 choices for the first, 3 choices for the second. How many interactions of those 2 columns do we have? What is 3 times 3? 9. I hope you can answer that one. Okay. So we must have at least 9 tests, and I claim we can do it with 9 tests. So can I do it with 8 tests? No. So in fact, this is optimal in the number of tests in this particular case. Okay. Yeah. So sometimes, actually I should take questions first. Are there any questions about this? Because it's related to your assignment. Okay. So it's kind of cumbersome sometimes to write out 3, 3, 2, 2, 2. And in fact, some of the arrays that I've been dealing with have 75 factors, 75 components, and it's kind of annoying to write them a 75 length tuple. So we sometimes use exponential notation here, where we basically just group the 3's together and group the 2's together. So the notation here says that 3 squared means that there are 2 components with 3 levels, which are the first 2 columns in this case. And then that there, for the 2 to the 3 part over here, that says that there are 3 components with 2 values. Okay? It's just a shorthand, yeah.
If it's like 3, 2, 3, you wouldn't be able to group them together then, right?
So what was your example?
Like if it's like, if the 3's and the 2's are spread out.
Oh, good question. So if I, for example, swapped columns 2 and 3?
Yeah.
Yeah. So what we're going to do is we're going to assume that all of them are grouped together because think about what we're doing. We're running the test when we're choosing everything from the first column, from the first row, sorry, all at once. So in effect, the order of the columns doesn't matter. It could be in the real system that we put the 3, 2, 3 like that, as you said. But for convenience, we could actually swap the order of the columns because we still have to check 5 choose 2 things anyway. The fact of whether we hit the 3, 3 at the beginning or 3, 3 somewhere else, it doesn't matter because we have to check them all anyway. Good point. We will return to that when we talk more about covering arrays. But any other questions about this? Okay, so we'll be actually talking most of the class about not mixed level covering arrays, but what are called uniform covering arrays. And the only difference here is that a covering array without the mixed on it is just that every single component has the same number of levels. So in the previous example, we had some that had 3 levels, 3 values, and some that had 2 values. Here, a covering array just has the exact same number for every single component. That's the only difference. Yeah, so I have an IE over here. All factors have V levels. So, yeah. Okay, yeah, so that's what we're going to be talking about most of the class. And what we want to figure out is this valuable quantity right here. So the covering array so this CAN thing stands for the covering array number. So that's what CAN is. How many of you have taken 304? Aren't you sick of TLAs? 3-letter acronyms? There are several in this class, so just a word of warning. So CAN TKV is, I'm going to tell you what the strength is, the T value. I'm going to tell you the number of components, the K value. And I'm going to also tell you the number of values that each component can take, which is V. And I want to figure out what the minimum number of tests is, the number of rows. So for the sort example, I claim that the 8-row example, when we looked at the pairs of components, was optimal. So I claim that CAN, so the sort command with T equals 2 implies that CAN 2K2 is equal to 8. Oh, no, sorry, not K, 18. So that's what I was just claiming. I didn't prove that was true, but that's what the result implies. So the first 2 is the strength, the T value, the number of components that we pick. The second value, again, is the number of those components, which is 18 for sort. And the last value, the other 2, is the number of values that each of the factors can have. So for sort, each one of them was a flag, so it can either be on or off, so it has 2 values. And what I claimed was that we can make an array with 8 rows. Okay, so then, and I can't do it with 7, I claim, so that the covering array number is equal to 8. Any questions on that? Okay, so it's just that we'll be exploring what the can value is. Yeah.
Can you say what the first two is again?
What's sorry? I can't hear you.
What the first two is again?
Yeah, so the first two represents the number of components that you pick. The thing that I was calling the strength earlier. So, and also in the example we did before with the 9 rows, we had the strength also being 2. So it's just the number of components that you're picking. So in this particular case, it's 2. But I gave the examples before where we could pick 3 different components. We can pick 4, we can pick 5, we can pick 6. So T in those other cases could be 3, 4, 5, or 6. Okay. Other questions about this? Okay. I mean, I can talk about applications in a second. Let's talk about your homework. So I put your homework on the course page. Not the course page, the Slack channel. So this is going to be due 1 week from today. And I may extend it depending on how far we get on Monday or something. So here, we're going to look at t = 3 instead of t = 2. So here, instead of picking 2 components, you're picking 3 components at a time. We're going to have 8 components in the example we're working with, and each of the components has 4 different values it can take on. Okay, so here what you're asked to do is just to do some computations. So you'll be writing a program, potentially in all 3 cases, where you're going to, actually, let's just go through it. So the first question is just, instead of like trying to be clever about how we're making the array, just make every possible row. So if we make every single possible row, then it must be a covering array because every single interaction must appear. We're making every possible row. So what I'm asking you to do is just do some basic computation. How many rows are you going to get? And then just provide a few rows. So that one should be the easy one. Question 2 is you're going to be, I'm not going to provide this to you, but you're going to write a covering array checker. So if you remember from what we were doing before, for this example, we had to check all 10 choices of 2 components, which had 10 of them. And we had to check for each one of them whether or not all the interactions appear. We made 1 check, you had to do the other 9. What I'm asking you to do for your homework is very similar. So what you're asked to do here is to look at strength T, which is 3 in this case, with 8 columns, which is K, and 4 symbols. So you can assume them to be any way you like, 0, 1, 2, 3, or whatever you want. And that what you do is to take in the input file in whatever way you want and verify that it is a covering array. And then basically you just print yes if it is, you print no if it isn't. And that's all you have to do for that one. Then for question 3, which is the last one, is to do a question that goes a little bit into research area. Not quite, because it's pretty simple to do, but it gets closer to it. So what you're going to do here is the exhaustive covering array that you made before has way too many rows. It has a lot of redundancy that you don't need. So what you're going to do is you're going to write a simple greedy algorithm to remove rows that are completely useless to you. And then what you do is you're just going to keep removing rows, and whenever you get to a point where all of the rows are necessary, quote unquote, then you just output the number of rows at that point. So, for example, if we go back to what we had before, Oops. So if I appended onto this array the row 1, 2, 0, 0, 0, is that row redundant?
Yeah.
Yeah, because why? That row appears somewhere else. What if I change this to be 1, 2, 0, 1, 0? Well, this row, 1, 2, 0, 1, 0, does not appear anywhere else in the array. It's a completely new row. But is it necessary? Do I need this row? Well, I claimed that the original 9 rows were a covering array. So do I need another row? No. So this row is completely useless to me because every interaction that appears in this row appears somewhere else. So I can eliminate this row. Okay? Any questions on that? So what you can do, so this is just my word of advice for this. Oops, let's go back to the homework. What you can do here is to look at all of the interactions and mark the first row that it appears. The first row that it appears. Could an interaction appear more than once? Yeah, it could appear more than once. And in fact, the example we did earlier had such an had an interaction that appeared twice at least. So what could you do? What you can do is mark the first time an interaction appears, and only the first time. Then go through all interactions, and then once you're done with all interactions, then if you have a row that is completely unmarked with values, has nothing marked, then that row is redundant. So if we look at our previous example, then if we look at the interaction 1, 2, for example, well, 1, 2 appears earlier in the array. So that means that we'll mark the 1, 2 in the earlier row, but not the later row. And if we find that we have a row which is not marked at all, has 5 unmarked things, then we can remove that row completely. Okay, any questions on that? What time are we? Okay, I have a few minutes. I can start the motivation. So why should we even consider covering arrays? So why would you even care about such a thing? So you may think, okay, well, these things are just used in testing, right? And testing is overrated. Testing's overrated, right? Wanting our software to work is overrated, isn't it? I don't think so, but there are quite a few people out there who do believe that. So what I want to convince you of is that that's not the case. That covering arrays do have other applications, not just in testing, which I think is already a good selling point, but it has other applications too. So this slide is just basically a summary of what a covering array could be used for in a real testing environment. So each of the rows represents a test, each column is a component, and here comes the sparsity of effects again, and I won't mention that again. So I'm going to talk a little bit about the other areas probably next time. But so I'll just do this slide and then we can quit for today. So note that we are going to work with a very restricted model and not one that has a whole lot of real world use. It's just that the ideas that we're going to develop for this model are very well applicable to real world testing. So the first one should be pretty obvious, that some components have more options than other ones. It's not the case that every single component has four values. It could be that some have 3, some have 4, some have 2. We sometimes want some tests that must be run. and also some tests that we actually don't need to run because they're run in some other process. There are some interactions we want to avoid, not just try to not include them, but actually avoid them, putting them in ourselves. Sometimes we want to have some components we want to have a bigger strength for versus a smaller strength. And sometimes, and in fact a lot of time, we want to actually find what the components are that are causing the fault, not just detect that. So I'll see you all on Monday.